Welcome back to Basic Electronics. In this lecture, our main focus is the small signal equivalent circuit of a BJT. First, we will explain the meaning of the term small signal condition. We will then derive the most basic form of the BJT small signal model and explain how it is related to the bias quantities. In particular, the bias value of the collector current. So let us begin. We are now in a position to look at the complete common emitter amplifier circuit shown here. And remember that we have actually considered this part earlier already when we looked at biasing of the amplifier. And now all of these things are added on top of it. So there is a coupling capacitor here going to the source voltage. Then there is another coupling capacitor, and that's how the load is connected, the load resistor. And there's a third capacitor which we call the bypass capacitor, and that's going from the emitter to the ground. We will treat this as the common reference node or the ground. And now let us see what the DC circuit for this amplifier is and what the AC circuit for this amplifier is. That's the DC circuit. And how do we get this? We recall that the capacitor is an open circuit in the DC situation. So this capacitor is an open circuit, and so is this and this. So therefore, this RL is essentially not in the circuit, Vs is not in the circuit, and this is an open circuit, and that boils down to this circuit here then. That's the DC circuit. What about the AC circuit? AC circuit is here. The resistors remain as resistors, as we have seen earlier. Capacitors also remain as capacitors. The AC source remains as AC source, and the DC source gets replaced with a short circuit. So that is what we have got for the AC circuit. What about the transistor? That is still a big question mark, and we have to, of course, tackle that question very soon. Otherwise, we really cannot proceed further. But what we see already is that this DC circuit is identical to the one that we considered when we talked about biasing. So the coupling capacitors ensure that the signal source and load resistor do not affect the DC bias of the amplifier, and it's a very, very big advantage because we don't need to worry about what we're going to have as a load resistance or what source voltage is going to drive this amplifier when we design the biasing components. And as we said, let's look at the purpose of CE a little later. That is not a coupling capacitor, that's a bypass capacitor. And just repeating it once again, this fact that the DC circuit is not affected by either Vs or RL enables us to bias the amplifier without worrying about what load it is going to drive. So that's a big benefit. And the next step now is to look at what this AC circuit, how that can be simplified. Here is the AC circuit once again. Now it turns out that the coupling and bypass capacitors are large, typically a few microfarads or even tens of microfarads. And at the frequencies of interest, their impedance turns out to be small. Let us take an example. Say C is 10 microfarads and F is 1 kilohertz. At this frequency, the impedance of the capacitor is 1 over omega C in magnitude. Omega is 2 pi times 1 kilohertz and C is 10 times 10 raised to minus 6. So that turns out to be only 16 ohms. And this impedance is much smaller than typical values of the resistances in the circuit like R1, R2, RC, RE, which are in the range of a few kilo ohms. And therefore what we can do is replace these capacitors CB, CC and CE with short circuits because their impedance is so small. And let us see what we get in that case. So this is what the circuit reduces to. What have we done? We have replaced CB with a short circuit, CC also with a short circuit, and CE also with a short circuit. And because of that, what has happened is this emitter has got effectively connected to the ground directly, bypassing this RE resistor like that. And now it is clear why this capacitor CE is called the bypass capacitor. Now this circuit can be redrawn in a more friendly format, and let us do that like that. And let us first check that these two circuits are actually the same. Let us start with the transistor. Here is the transistor. From the base we have Vs going to ground, R1 going to ground and R2 going to ground. What about this case? Here is the base. We have R2 going to ground, Vs going to ground and R1 also going to ground because we have a short circuit here. Alright. What about the collector? From the collector we have RC and RL connected in parallel and going to ground. Here from the collector we have RL going to ground and also RC going to ground. And the emitter is connected directly to ground in both cases. Alright, so these two circuits are indeed identical and we can proceed further. The next question now is, what is the AC description of the BJT? So let us look at that in the next slide. Okay, so the question we want to answer now is what is the transistor behavior when sinusoidal input voltage is applied and superimposed on DC bias value. In particular, we will look at the base emitter voltage of this form where V0 is a constant, let's say 0.65 volts corresponding to a forward bias, and on top of that there is this sinusoid riding with a frequency of, let's say, f equal to 1 kilohertz. And in this graph we are plotting IC, the collector current, the total collector current, as a function of time, and we are only showing one cycle of the input waveform which corresponds to 1 millisecond. Let's look at these curves one by one. So this blue curve corresponds to VBE equal to V0 and with no sinusoidal part there. So just V0 constant, and that's why the collector current is also a constant. If we apply VB equal to the same constant plus Vm sin omega t with Vm equal to 2 millivolts, this is what we get. If we increase that amplitude Vm to 5 millivolts, this is what we get. And if we increase it further to 10 millivolts, this is what we get. And as we are looking at these closely, you will surely notice some difference in the shape of these three curves. As VBE varies with time, we expect IC of t also to vary with time, and when VBE increases above the base value V0, then IC will go above this base value, that is the DC collector current corresponding to base emitter voltage of V0. And when the base emitter voltage goes below V0, then we expect the collector current to go below that IC DC value here, and that is what is happening. Now in this case, when Vm is 2 millivolts, we can see that these positive and negative excursions are equal, and that is what a sinusoid should look like. But if we increase Vm to 10 millivolts, we see that this positive excursion is larger, this difference here, than the negative excursion. And clearly, therefore, there is some distortion in the collector waveform for Vm equal to 10 millivolts. So that is the first point we make. As the VBE amplitude increases, the shape of ICT deviates from a sinusoid, and that causes distortion. Now suppose we were to write an equation for this IC of t, only the time varying part of this IC of t. What would that look like? It would be sinusoidal, and its amplitude would be that height over there. So it would be some IC cap sine omega t, and that's exactly the same form as the time varying part of the base emitter voltage. So in other words, the time varying parts, or the sinusoidal parts of the collector current and the base emitter voltage, are proportional to each other, and that is the second point we want to make. If VBE of t, that is the time varying part of VBE, is kept small, then IC varies linearly with VBE. And the next question that arises is how small? Let's look at that in more detail in the next slide. Here is the graph again of the collector current versus time, and the base emitter voltage is a constant, which is 0.65 plus Vm sine omega t, and the frequency is 1 kilohertz. And the base collector junction for these calculations was assumed to be under reverse bias. The exact value of the reverse bias, of course, is not important. Now in these conditions, that is in active mode or in the linear region, the device model, as we have seen before, is given here: the base emitter diode and then the current controlled current source. If this is IE, that is alpha times IE. So we are of course very familiar with this model by now. Let us start with VBE, the instantaneous base emitter voltage, equal to the constant part and the time varying part. In this case, Vm sine omega t. And the constant part, of course, we call as the bias, and the time varying part is the signal. And similarly, the collector current also would be a constant part plus a time varying part. And assuming active mode, the collector current is alpha times IE of t. And what is IE? It's IES e raised to VBE by VT minus 1. This is the total instantaneous base emitter voltage. That is the total instantaneous emitter current. And this is of course simply a special case of the Ebers-Moll model, as we have seen earlier. Now since the base emitter junction is forward biased, this term will be much larger than this one here, and we can simply ignore that one and get IC of t is equal to alpha times IES times exponential VBE divided by Vt. It's the same as that one, except we have not written that one there. equal to alpha times IES. Now this VBE, the instantaneous voltage, we are going to substitute with VBE plus the DC part plus the time varying part, like that. And now this is like e raised to a plus b, which is e raised to a times e raised to b, and that brings us to this equation. IC of t is alpha ES times e raised to VBE by VT. This is the constant VBE, or the bias value of VBE, times e raised to VBE of t divided by VT. This is the time varying VBE, this part here. Now if VBE, the small v sub small be, is 0, if this time varying part is 0, then what do we have for the base emitter voltage? It is simply this constant value, in our example 0.65. And then if we substitute that here, IC of t, this becomes 1, and we are left with alpha times IES times exponential VBE by VT. So it's 0.65 divided by VT. And that is the bias value of IC with no signal, and that is shown here in the dark blue curve, just a constant straight line. So if VBE is 0, if the signal is 0, then the total instantaneous current, collector current, is the bias value of the collector current, that is IC, capital I sub capital C, the DC part of IC here, is alpha times IES times e raised to VBE by VT. And now this part is also appearing here, and therefore we can say that IC of t is, instead of writing this expression, we just write IC, and that multiplied by e raised to VBE by VT, where VBE is the signal VBE. So from all of this algebra we get IC of t, that instantaneous collector current, is the DC or bias collector current multiplied by e raised to VBE of t divided by VT. So in this term there is only the time varying component of VBE. In this term there is only the constant component of VBE. Let's remember that, and let's go further with this. Here is the relationship between IC and VBE. Once again, this quantity is the total instantaneous collector current. It includes both the DC and the signal collector current. This capital I sub capital C is the DC or bias value of the collector current. This VBE is the signal base emitter voltage. It does not include the bias or DC base emitter voltage. Alright, let us now take a specific example, say this one, where VBE is given by Vm sin omega t with Vm equal to 2 millivolts. Let us define a variable x as VBE by Vt, where Vt is the thermal voltage, 26 millivolts, and Vb of t in this particular case is going to be limited to 2 millivolts in magnitude. So this magnitude of x is always going to be smaller than 2 millivolts divided by 26 millivolts, say 1 by 12. Alright. Now what we will do is expand this e raised to x using the Taylor's series, and this is what we get. Since our x is small in magnitude compared to 1, we can ignore terms like x squared by 2, x cubed by 6, and so on, as compared to x, and therefore we get IC of t as approximately equal to IC times 1 plus x. So in summary, if x is small, that is if the amplitude of VBE, the signal part of the base emitter voltage, is small compared to the thermal voltage Vt, then we get IC of t, the total instantaneous collector current, equal to IC, which is the DC or bias collector current, times 1 plus X, and X is VBE divided by Vt. Let us now write the total instantaneous collector current as the sum of the DC collector current and the signal collector current. So this is our left hand side here, this is the right hand side. The DC collector current cancels out and we get IC of t, the signal collector current, equal to IC by Vt, where this IC is the DC or bias collector current, times the signal base emitter voltage as a function of time. What does this equation say? This equation says that the signal collector current is directly proportional to the signal base to emitter voltage, because these quantities are constants. Note that the collector current does depend on the base to emitter voltage, but only on the constant part of the base to emitter voltage, namely 0.65 volts in this case. So this relationship looks like IC of t equal to K times VBE of t, where K is simply a constant which does not depend on time. What are the implications of this equation? It says that if X is small, that is, if the amplitude of the signal base to emitter voltage is small compared to Vt, then the signal collector current is directly proportional to the signal base to emitter voltage. If VBE of t is sinusoidal, as in this case, and if the amplitude of VBE is small, then we expect the collector current also to be sinusoidal. And that is indeed what we observe in this case, which corresponds to an amplitude Vm of 2 millivolts for the base to emitter voltage, which is small compared to the thermal voltage, about 25 millivolts. Now let us take this case where the amplitude of the base to emitter voltage is larger, 10 millivolts. The maximum value of X now is 10 millivolts by 25 millivolts, that is 0.4, and that is not small anymore with respect to 1. So what that means is we cannot ignore these higher order terms with respect to X, and that shows up as distortion over here. Now this condition, in which the variation of the base to emitter voltage is small compared to the thermal voltage Vt, is called the small signal condition. And it is very important to keep in mind that this equation which we have derived is only valid if the small signal condition is satisfied. So it is under this condition that we will now derive the BJT small signal model. And that brings us to the small signal model of the BJT, and it is now clear why it is called small signal, because the base emitter signal voltage must be small as compared to the thermal voltage Vt. And then we have this relationship that we saw in the last slide. Now this equation can be rewritten as IC of t, the signal part, equal to VBE of t times Gm, where Gm is IC by Vt. Now Gm is a constant because IC is a constant for a given bias condition, that is for a given bias value of the base emitter voltage, and Vt is a constant. So this Gm, which is IC by Vt, is called the transconductance parameter of the transistor. And it's very, very important to remember that it is not an absolute constant, because it depends on the bias condition. In particular, it depends on the bias value of the base emitter voltage. To summarize, we have addressed a very important issue in this lecture, namely the small signal condition in the context of a BJT and its implications. We have derived the hybrid pi model of the BJT under the small signal condition. In the next class, we will put all these findings together and look at the complete small signal circuit for the common emitter amplifier. Until then, goodbye.